Great. So thanks for having me, everyone. I am Jim Purbrick. I work at Facebook London on Oculus VR and social VR products and technologies with Sunil and Mike Armstrong, who you may have seen at React Europe before. I'm at Jim Purbrick on Twitter and basically everywhere else, so you can find me. And today I'm going to talk about some interesting things we've done replicating React stores across the network to build shared social VR experiences. So this kind of conversation started at Oculus London when Mike Armstrong was working on ReactVR. I was working on Oculus Rooms, which is our shared social space for you and your friends to hang out in VR. And so then Mike and I naturally started talking about how you might want to build shared social experiences with ReactVR for multiple people. And so what we were thinking about is we wanted to make this possible in a way that felt idiomatic to React developers. We didn't want you to have to know about React and ReactVR and about multiplayer game programming. We wanted it to feel natural. And ideally, we wanted to make it completely invisible. So you could build a ReactVR experience, and if it worked for you as a one-player experience, then it would work for you as a multiplayer experience. Because one of the things that's really hard about building multiplayer games or multiplayer shared experiences is that it's really difficult to test. You have to have either complicated test setups which simulate a second client, or you need to actually have a real person who you can get into the experience and test it together. So we wanted to make this really tight development loop where you could just build stuff, kind of hot reload it onto your Oculus headset, immediately see the changes to your JavaScript and your ReactVR application, and know that it was just going to work when you had multiple people in that experience. So that was what we were trying to do. So I'm sure many of you have seen this equation before. Hands up if you've seen a version of this equation before. Yep, most people. I stole this from Sunil, so I thought lots of people had seen it before. So React's big idea is you make the view a function of the application state. So you define this function, which takes some state, creates a view, and once you've defined this function, React takes care of updating your UI. And this is kind of the equivalent equation for Redux. Who has seen this one before? Okay, a bunch of other people. Good, awesome. So Redux adds this extra function, which makes the next state of your application a function of your current state and some action applied to that next state. And so you define this function in terms of a bunch of reducers that you compose together to build your application logic, and then you dispatch actions to your store as part of your UI interactions, and then the actions get reduced to produce your next state. So in return for agreeing to this deal with Redux, in return for agreeing to only change your state via this mechanism, Redux makes it really easy to save and load your application state. It makes recording and replaying your applications easy. It makes time travel easy. It makes undo and redo really easy. There's a bunch of things that, that Redux gives you in return for you agreeing to only change your state in this way. So let's look at some of the pieces of Redux and how they might be useful for building shared VR experiences. So here are like the building blocks of Redux. At the top here, we've got an action, and this is an action which will lock a door. Then in the middle, we have some state. So currently, our door is unlocked. And then at the bottom, we have a reducer, which takes a state and an action. And if the action type is lock, then the new state will have the door locked. Right? Super, super simple. So it turns out that the same features that make some of the other benefits of Redux possible also make it really easy to network Redux applications. You'll notice that the action is just a simple JSON type that we can serialize across the network. The state is just another simple object, JSON object that we can serialize across the network. And the reducer is side effect free, which means that if, for example, we apply an action, so we reduce an action to produce the next state, and then we realize we got it wrong, we can potentially easily go back to a previous state. We can reapply the same action to a different state or reapply an action multiple times. And if there are no side effects in the reducer, then we know we can get away with that, right? We can instantaneously rewind and rewrite history once we get more information, and we know that everything else will be okay as long as our reducers are side effect free. So This is really encouraging. We looked at these pieces of Redux and we thought, okay, this is good. We can send actions and we can send state across the network. And then there's another really interesting part of Redux, which is its support for middleware. And the way middleware works is that you create an action as a result of some user interaction. You dispatch it to your store, but then you can also install middleware between the point at which you dispatch the action and the point at which it gets reduced. And so this was interesting because we thought, well, okay, if we can build all of the machinery to synchronize Redux stores across a network as middleware, then potentially you don't need to change your application at all, right? You write your single user application, and then you install some pieces of middleware when you set up your store, and then that middleware will take on the job of sending actions and state between different copies of your store, and then it will keep them in sync, and it will deal with all of that multi-user stuff for you. So let's look at how middleware might work, and let's look at a really naive first version of how we might go about synchronizing Redux stores. So this is a very simple middleware. It takes a function which will send actions to all other copies of this store, so all other clients that are connected to our shared experience. And then it will just return next action. So that means it will apply the next middleware. If there's no other middleware, it will just dispatch this action. So this is a super naive implementation. We assume that the send function will send the action, and then if you receive an action over the network, you'll just dispatch it as if it had been generated by your own user interface. So this is a super naive version of what we might want to build, but of course it doesn't work. Because if you have two clients and they both generate actions, imagine one client is generating a lock action and the other client is generating an unlock action, and they both send it to each other, and those messages cross on the wire, and then they reduce them at the other end, then we'll end up in an inconsistent state where one of our clients will decide that the door is locked and the other one will decide that the door is unlocked. So, nice try, doesn't actually work. So let's try again. So this version implements a kind of dumb terminal consistency mechanism. So imagine you've SSH'd into some server, you're typing on your keyboard, all that's happening is key presses are being sent to the server is effectively processing those key presses and sending the information back to you. So that's effectively what this is doing for a networked Redux application. So we're passing in a couple of extra functions here. The first one, this isMaster function, just returns true on one of our clients, so we'll arbitrarily pick one of our clients to be the server, to be the master client. And then we have this isValid function in addition to our send function. The isValid function is really the only change we've made to the normal way that you program Redux. And what this does, normally if you build a Redux application, you'll write some user interface logic, and before you generate an action, you will work out if this action is valid, right? It's only valid for me to copy some selection if I have something selected. So I will only allow that action to be generated if it's appropriate and valid for that action to be generated. So what we're doing is we're saying, take that logic that you normally put in your user interface, put it in an isValid function, and pass it to this middleware. And what isValid does is it allows the framework to say, is it valid for me to reduce this action given the current state of the store on this client? That's all it's doing. So you're not required to write any more logic. You're just required to package up the logic you would have written anyway and pass it to the framework as this function is valid. So then, given those three functions, the rest of the consistency mechanism is really simple. It basically says, if I have generated an action locally, then send it to the master. If I get an action from the master, then apply it to my store. And what this means is that every single client is then reducing the same sequence of actions in the same order, and so therefore it's ending up consistent. So great, it works. We now have Redux stores synchronized across the network. However, there's still a problem with this. The big problem is we've introduced round-trip latency to every single action that we create and reduce. And this is a problem in VR. It's also a problem on the web. A lot of the JavaScript we write allows us to do local processing so we can avoid these round-trip latencies to the server. And we've just built a middleware that introduces round-trip latency to the server. So this is actually one of the kind of motivations of the work we've done here. We've got this game. This is Oculus Rims running on an Oculus Go. And you can see it's a multiplayer matching pairs game. So you can click on a You can click on one of these tiles, it will flip over and show an image. If you flip over 2 images that match, then the tiles disappear and you get a point. So this is a really interesting example because it's multiplayer. There is opportunity for conflict because we can try and click on the same tile, but only one of us is allowed to flip it over. But we also want immediate feedback. We don't want to have to click on a tile, wait for an action to go to a server, come back to a client, and then for the tile to flip over. We want it to immediately happen as if we are co-present in a shared VR experience. So this is really what we want to make work. We don't want to have dumb terminal consistency. We want to have some way of immediately showing the effect of an action, but also dealing with conflicts when they happen, when 2 people do something at the same time that's conflicting. So this is what we want to make work. And actually, the original version of this game was built in Unity, and we had to solve a lot of these problems, right? The original version used a standard Unity network library. It would send actions to a server, we would get the actions back, and then when we were testing this, we were like, the user experience is bad, we want to predict updates. So we had to build this kind of custom prediction optimistic update logic specific to this application. It was very difficult to fix that logic because it's complicated. There are lots of edge cases. It works, you know, the problems come up are problems of concurrency and distribution. And if you test this game with a single player, you don't find those problems. You only see those problems when multiple people are playing the same game at the same time. So this is really what we were trying to solve when we set off to build this stuff. So let's have another go. So this is another middleware. It takes the same isMaster function, the same isValid function, the same send function. It adds another function which is sync state. And this function that you have to pass in basically just gets the current state of the store and will create an action to synchronize everyone else to this state that I'm giving it. So now effectively we can build a very simple naive middleware which goes, okay, as soon as I get an action, doesn't matter where it's from, whether it's a local action or a master action, I am going to apply that to my local store. So I've got rid of the latency. I'm immediately going to see the effects of my local actions. And then if I'm the master and I notice that I've seen an action that is not valid, if I've seen an action that I can't reduce given my current store, but somebody else has already reduced it and sent it to me, then I know I've seen a conflict, right? I know that someone has reduced this somewhere locally, then they've sent it to me and I'm not going to reduce it. So I've seen a conflict. And so if the master sees one of those conflicts, then it's going to go, okay, I'm going to synchronize everyone to my current state. We're effectively going to all rejoin the simulation together. We're going to reset to a start point that is consistent, and then we're going to play this game again until there is another conflict. And so basically what you see as an effect of this mechanism is immediate interactions, but then occasionally you see kind of glitches, you see discontinuities where the simulation gets reset and then starts going forward again. In practice, the glitches are the kind of discontinuities are very rare, because most of the time people aren't conflicting. If you imagine that pairs game, most of the time people are just flipping separate pairs and there are no conflicts. The actions come to the master just says, yeah, I can reduce this, everything just carries on going forward. It's only when 2 people try and flip the same pair at the same time that you get a conflict and the master has to decide which of these actions gets reduced and which of them doesn't get reduced. So we felt this was potentially a thing that could work, so we built a web version of it. So this video shows 2 browsers running the initial ReactVR or React 360 implementation of pairs. They're connected over a very high latency network, so you can see these discontinuities, and you can see the effects take place. You can see sometimes, you look at the scores on the bottom row, sometimes the scores get out of sync, and then they immediately, or later on, they resync and become consistent again. And that's this eventual consistency happening. The simulations are allowed to get out of sync, then the master notices they're out of sync, and then it resets them. And the other thing that's interesting about this example is that you're seeing it, I'll replay it again. You see the actions, hang on. You see the actions, hang on, this is not as simple as it should be. Let's see if I can play the video again. No, okay. So anyway, if you remember, you'll have seen that actions happen very quickly, and that's one of the benefits of the Flux architecture which Redux implements, is that we're decoupling the state changes from the user interface, right? So in that example, I wasn't clicking on a square to flip a pair. I had a scheduled callback which was just generating actions and throwing them at the store as if they were generated by the user interface, which meant I could get two browsers up and I could just watch as these actions get generated. And because I have this isValid function, I can just throw away any actions that aren't valid. So it's a very easy way of me to randomly generate actions, throw them at the system, and see what happens. So I can just watch the game unfold, and I don't need to, I don't need to click around on two clients at the same time, which is really kind of beneficial. So let me get to the right slide again. So when I ran those two clients over and over again with these auto-generated actions, I would see that sometimes the simulations weren't eventually consistent, right? Sometimes the thing would end and the scores would not be the same. And so there was clearly a problem. Now, Redux makes debugging these things pretty easy because you can just go, okay, I'm just going to log all of the actions to the console, I'm going to open the consoles, and I'm going to compare the list of actions that were reduced on each side of the application. But even then, right, when you need to have dozens of actions being applied before discontinuity happens, it's actually difficult to find out the point at which things broke down. And so we kind of we ported the browser version of this test with two browser clients into a testcheck.js property-based test. So if you haven't looked at testcheck.js, it's amazing. It allows you to do property-based tests for JavaScript and React applications. And it works really, really well with this kind of Redux, and with these Redux applications because of the decoupling of user interaction from changes, right? So in the same way that I could generate random actions in my browser client, I can now generate lists of actions, dozens of random actions, and I can, in a test, I can reduce those on a store pretending to be the master, I can reduce those on a store pretending to be a client, and then I can check for a property. And in this case, the property I care about is that I want to make sure that these two simulations are eventually consistent, that at the end of all this reduction, regardless of whether you're a master or a client, regardless of which actions you got in which order, you have the same state as the master. And so I couldn't fit the whole test onto this slide, but I've got some of it here. So you can see at the top, I'm pretending to be the master. I'm generating a sequence of actions from client A. I'm dispatching them to the master. I'm generating a sequence of actions from client B. I'm applying them to the master. And then I'm storing the master state at the end. So that master state equals store.getState. That's what I want all my other clients to match at the end of this. And then the middle section here is I'm doing the same thing, but I'm pretending to be client A. And so what I do is I reduce all of my actions. So effectively, I'm predicting all of the actions that have been generated at client A. And then I'm reducing all of the actions that the master sent to all of the other clients. And then I'm expecting at the bottom that the state of my store is equal to the master state. And this is incredibly, incredibly powerful. This is actually the thing that makes this technology useful, right? All the rest of it is pretty trivial. But the fact that I can take any application, I can randomly generate all of the actions that the application might generate. I can then simulate in a test thousands and thousands and thousands and thousands of combinations of actions across multiple clients with different consistency mechanisms and make sure that they're eventually consistent. This test here has saved months and months of debugging and testing with multiple clients. So if you're ever doing any of this kind of stuff, if you're ever trying to keep things in sync and you're trying to have optimistic updates and eventual consistency, then please write property-based tests and save yourself months and months of time. So we wrote the test, we found the problem, we then came up with replay consistency. This is the final middleware I'm going to show you, and this is what we're currently using. And the way this works is instead of just letting everyone apply all of their stuff locally and then having the master synchronize everyone, the problem we found with that policy was that it only worked if every sequence of actions that causes a conflict also caused a conflict in the reverse order. Because what we found with pairs is that if the master didn't see a conflict, then it would have just assumed that everything was okay. So even if a conflict had occurred because of the ordering on one client, if the master didn't get that ordering, it wouldn't see a conflict and it wouldn't resync the state. So this basically puts the logic for detecting and fixing conflicts in the client, which is actually good because we're now distributing the problem across all the clients anyway. So the way this one works is that If we're the master, it's really simple. We're just going to say, is this action valid? If it is, send it to all the other clients. If we are not the master, if this was a locally generated action, then I'm going to reduce this action. I'm going to send it to the master, but I'm also going to append it to a list of predicted actions. So these are actions that have been generated locally that I have applied locally, and I've shown to the person using the application. But I'm not sure if they're valid, if the server thinks they're valid yet. So I store them in a list of predictions. And then whenever I get an action from the master, I will instantly reset my state to the point at which I started predicting results. And then I will apply the master action, which is the next sort of canonical valid action from the master that everyone is going to apply. And then I'll reapply my list of predictions to find out if my predictions are still valid. If my predictions continue to be valid after I've applied the master action, that's great, I can keep predicting them. If my predictions stop being valid, then I should throw them away, because I know that the master has thrown this action away, my prediction was invalid, I can't predict it anymore. And so then over time, one of two things happen. Either I get an action from the master which conflicts with one of my predictions and I throw the prediction away, or I get an action from the master which is my action, and I find out where in the total serialization of actions that need to be applied at every client, I find out which spot in that sequence my action should go, I apply it there, and then I can throw my prediction away. So over time, this becomes eventually consistent. I can predict all of my actions, and it doesn't matter which order the master sees things, because the prediction and reconciliation is done on each client based on the order in which they applied their actions. So this works, and you can test it with the property-based tests. You can run tens of thousands of different sequences of actions, and you find out that all the clients end up eventually consistent all the time. So that's basically where we've got to. I'm now going to show you some videos of what we've built with it. So this is the first game we built with replicated Redux. So this is the trivia game in Oculus Rooms, running on an Oculus Go with one of the other people from our team. And the idea here is that everyone gets shown a question, and whoever answers quickest gets the most points. And the reason we wanted to have a time element in is because we wanted to have some racing, we wanted to have some conflicts to prove out that our kind of optimistic updates and eventual consistency works. So you can see we're answering a bunch of questions. I'm generally answering faster, and so I'm getting the most points, which is great. So that was the first game we built, and it was largely, you can see the UI. The UI is built with ReactVR, but it's a 2D UI. And so mostly this game is about proving the networking technology. So this is the new hotness. This is Boggle, which is licensed from Hasbro, running inside Oculus Rooms on an Oculus Go again. And this is going to be launched on Monday. So if you win the Oculus Go, you'll get to play this on Monday on your shiny new Oculus Go. And as you can see, this is way more sophisticated. So ReactVR here is positioning 3D objects. We're interacting with 3D objects. You can see animations. We're animating 3D objects in our 3D environment, all using ReactVR. And so this demo is the ReactVR is not just for 2D UIs demo. We're actually getting very sophisticated applications that we can build and embed inside 3D environments. So the environment and the avatars are built with Unity in C#. Then effectively there's a table in that environment, which is the table on which the ReactVR applications will run. And everything you see on the table, the Boggle cubes, the animations, sound effects, everything else is built with ReactVR. So where have we got to, and what happens next? So the point where we are at the moment is that we can build replicated Redux to build network synchronized interactive ReactVR applications within other 3D environments. We can build tabletop games. We can build shared interactive 3D maps, for example. This is Mike Armstrong's vision of the future, where people are deciding where they wanted to go in a city together. We can build vending machines. We can effectively take some chunk of your virtual environment. We can say that chunk is a ReactVR application. You can interact with it. It can change the world around you. We haven't really talked much about the avatars you've seen, or about things like physically simulated objects, like boxes bouncing off each other, that kind of thing. And so the networking approach would definitely apply to avatars and physically simulated objects. This approach is actually very similar to the kind of framework I built for VR, or helped build with C++ for VR a couple of decades ago, called Massive 3. And the things you change there is you would, because avatars change continuously, and because physical objects change continuously, you would probably use unreliable transports, you'd use UDP, unreliable messaging, you would use kind of delta states, right? So you don't want to resend actions that applied 10 minutes ago if the object is still bouncing around. You want the latest version of that state. So there are some things you would change, but broadly this approach would apply to those applications. You might not want to use the full React reconciliation diffing step if you know that your objects are changing every single frame and moving around the whole time. But then again, you know, one of the original inspirations for React was the Doom 3 engine, and so actually you can get quite a long way building interactive applications with React as well, especially if you start using the things that Christoph was talking about, where you can effectively declare animations and you can kind of declare behaviors that you want to happen, and then you can pass those from JavaScript to the native thread to avoid kind of back and forth and round trips between the two threads. So you can do a lot. I think you can do a lot with this, and I think we will be doing more and more with this above and beyond kind of these network synchronized games that we have now. And if you think about it, avatars currently work a lot like shared mouse pointers. So you in the same way that you move your mouse around so that you can find the button you're going to press, in VR, you move your hand around to find the button you want to press in VR, and when you see somebody else's hand, it's effectively you're seeing somebody else's mouse pointer. And so if you imagine the same kind of split you have between discrete events when people click on a button and continuous events when people move a mouse around, it's kind of a similar thing with avatars currently. In many experiences, the fact that your avatar positions are controlled by some other application, and your application logic is just getting these discrete events when the avatars actually do something. In many cases, that's okay. But you could also imagine applying impulses to physical objects, so you could make pinball machines where I press a button and a ball starts shooting off. You could also imagine subjective modifications to remote avatar positions to allow things like high fives and handshakes and people dancing together. So I think one of the areas we're looking at the moment is what happens at the boundary. What happens at the boundary between these kind of embodied avatars in an environment that are changing continuously and our kind of applications which are working in terms of discrete events to produce discrete states, which are then rendered as a view via React. So there's a bunch of more stuff that we want to do here. And in case you're wondering, you might be thinking, wow, this is all really cool, but I don't build React VR applications. I don't build VR applications. Like, how is this relevant to me? Well, people have been talking about building kind of collaborative computing systems for decades, since the mother of all demos. And so this is definitely, these kind of approaches are definitely useful to not just React VR applications, but for any kind of React application where you want to keep multiple clients in sync, where you want people collaborating on a shared document or some other kind of shared system where people need to share the same view of an application across a network. So it's definitely applicable to those kinds of things. The things you might want to do differently in those environments are that instead of reconciling conflicts, you potentially want to kind of reconcile in a kind of more collaborative and additive way. So for example, while in a game, maybe only one of us can score a point and therefore someone wins and someone loses, in a collaborative editor, you want to have effectively actions combined with each other. So if I edit some text over here and you edit some text over there, we want to combine it in a way where none of our edits are lost. And so those kind of approaches are much more like operational transform style approaches used by Google Wave, but you could imagine building some middleware that instead of going, I'm going to reset my prediction and then kind of roll forward in it with a different history, which is what we're doing here, which is what games like Half-Life do. You can imagine taking a more operational transform approach where you kind of combine two actions together to produce a composite of that action, which is what Google Wave and operational transforms do. And it's also, you potentially want to start looking at whether you can use conflict-free replicated data types to allow two people to work on the same data structure at the same time and to combine the effects of their manipulations instead of kind of trying to figure out who won and who lost. So you might want to change some stuff, but a lot of what I've talked about here is relevant to those kind of applications as well. So links. All of the code you have seen and all of this, the web example that I showed you in the browsers is available in the React 360 GitHub, including all of the middleware. I've written a bunch of blog posts about this work on jimpurbrick.com, which goes into a lot more detail. There are other projects available which explore these kind of ideas. So Logux, Redux Swarm Log talk about synchronizing actions between React stores across the network. Redux Optimistic UI talks about applying actions optimistically locally before you've got verification across the network. And then there's lots of stuff on Wikipedia about operational transforms, conflict-free data types. So hopefully that was interesting. Hopefully it will be applicable to some of your work. And hopefully some of you will build cool stuff with ReactVR and Redux in the future. Thanks a lot.